Afternoon, everyone. Hope everyone stays awake after the post-lunch slot. So I'm Pete Burnap. I lead cybersecurity research at Cardiff University, and I'm here giving a talk with Matilda Rhodes, who's a colleague and a security researcher in the team. So it's not an academic talk, don't worry. It's really around what we're doing in the area of cybersecurity analytics. So I'll just give you a bit of an overview of what that is, what we've been doing in the area of active cyber defense. Matilda will give a bit of a demo as well. And hopefully you'll get an idea of the importance of some of the work that we're putting into practice. So really quick bit of context in terms of the cybersecurity landscape. Obviously, the UK has a cybersecurity strategy, which is to keep the UK safe and secure. It also has an industrial strategy, one pillar of which is artificial intelligence and the data economy. Part of the National Cybersecurity Centre is active cyber defense, seeking out and doing something about attacks. So essentially at the university, our research is about pulling all this together. And we do a lot around AI, particularly machine learning, but also moving into more genuine, cognitively aware AI for detecting and mitigating cyber attacks. So just a quick nutshell overview. This is a slide I normally use to introduce the sort of themes of the research. I won't go into all of it, but to give you an idea of what cybersecurity analytics is in our view. So starting on the end towards me, you've got risk assessment and modeling. So typically risk assessment you'd normally do, to find your assets, look at the threats to those, or vulnerabilities of those, threats to those vulnerabilities, put them all together maybe with an impact number that might be historic or maybe just a finger in the air, and that, you get your risk assessment, you can use that for compliance, maybe a bit of operations, but generally it's not particularly dynamic. So we've done some research in the area, kind of flipping that on its head, thinking more about goals and goal-oriented approaches, which are perhaps more intuitive. You don't need to know everything that could go wrong, which is a big issue with risk assessment. And goals tend to have dependencies, so you can capture dependencies between your assets and your goals underlying them a little bit more. So we've done some research in that area. Bit in the middle is about communication, governance, decision-making. This is where we tend to draw in psychology experience and criminology, who talks to who around attacks. And the bit on the end is the bit that we're going to talk about today, which is the AI or machine learning-based attack detection used in different types of behavior in different environments. So the bit cutting through it, mobile, IoT, cloud, desktop, operational technology, and going forward into connected vehicles, and also even the security of AI itself. So the bit cutting through it varies as technology emerges. Bit across the top, all about human factors, why people do stuff, how people do stuff. And a key important factor is if you're using data to drive machine learning algorithms to detect attacks, so having that understanding of what would you actually be looking for. So bringing a little bit of human knowledge into the equation so that you can actually interpret the output of these machine learning algorithms. So I won't go into the details of everything that we're involved in, but bottom right-hand corner there, you've got the Airbus Centre of Excellence in Cybersecurity Analytics. So the work that we're going to talk about next is how we've transitioned some of our academic stuff into practical applications at Airbus and really driving forward innovation in security operation centres. So one of the problems that we're working on is basically moving beyond traditional AV. So we all know that signature-based detection has its limitations, as does static analysis. You've got things like APTs, but even just more general malware is becoming more sophisticated, obfuscating code, flipping code around, code encryption, hiding API calls, in-memory execution, all the kind of stuff that makes it actually quite difficult to detect using a static or a signature-based approach. So this is what we're kind of trying to address that. So we're trying to say, well, what does a future SOC look like where you involve some sort of AI or machine learning in this kind of environment? So we're moving towards stuff that's a little bit harder to obfuscate, so system-level activity metrics. So there was a paper that came out following it's called the Big Four APTs, and it basically suggested we need to do more with stuff that you can't hide. So if you want to do something as an APT, you have to interact with the underlying machinery. That'll leave a footprint and a trace. So anything like CPU, RAM, data I/O, processes created, and all that kind of stuff has to happen on the machinery in order for you to be able to do something and achieve your goal as an attacker. So we've been working with using that data as a footprint for behavior such that we can actually then use data-driven approaches to detect malware and distinguish between malicious and benign. So in a way, if you think about a whole bunch of behaviors that are malicious and a whole bunch of behaviors that are benign and normal, we're trying to create DNA profiles of both to be able to, A, distinguish between malicious and benign, but B, try and work out which DNA is this most similar to. So you can start to do things like campaign profiling, better understanding what's actually going on in a particular piece of malware while you detect it. So the starting point of our innovation in cybersecurity analytics is we took thousands of samples of malicious traffic, or actually code executables, PDF and PE32s. We ran these in a sandbox environment, which fully aware of the fact that there are limitations of what you can capture in those environments, given that it's not on bare metal and there may be evasive features within that. We took then thousands of samples of clean, normal traffic that you'd expect to see on a day-to-day basis, and we developed a whole bunch of behavior, and we created two what we call maps. This method is called the self-organizing feature map, and what you can see here is two maps, one representing all the good behavior, one representing all the bad behavior. So within that sandbox environment, we collected the system metrics, the bit that was left behind while it was running, every second for 5 minutes. And every second's data is put onto one of these maps. Starting point is an empty map, totally kind of blank, and you just plot the first bit of data wherever you want. Then you get the second setting, and you put that on there, and that will end up quite close to it, because it's fairly similar. And then the third, the fourth, the fifth, over time with thousands and millions really of data points, you start ending up with similar behavior clustering together and different behavior pushing apart. So that's why it ends up looking a bit like a dispersed set of nodes. So the lighter the color on this, the more frequent we see that behavior, and the darker the color, the more new that behavior is. And what it leads to is this concept of sort of fuzzy neighborhoods where you can see this is similar to stuff we've seen before, but a little bit different. So again, if you're actually flipping the code around, doing different things, but you're still actually achieving the same goal, it still allows us to kind of model that in this environment. So if you actually put this into practice, what you would see is every second, new bit of behavior coming in, working out which map does this sit on. Is it fit better with the good behavior or the bad behavior? And then once you've worked out if it's better with the bad behavior, you plot it on that map, and then it'll tell you, well, actually, which node does this sit on better? So you get good, bad occurring. So you can see it by eyeball initially that it's actually landing in a lot of the frequently seen bad activity area. And over time, it's building up basically a profile of whether it's good or whether it's bad. But what it's actually giving us is an XY coordinate. So we transformed all the continuous data about the behavior into essentially an XY coordinate that represents either a good behavior or a bad behavior, and an XY coordinate, which we then use in other algorithms to tell us whether it's malicious or benign. So this has actually worked out pretty well. It's around about 94% accurate when tested on a whole bunch of other samples that we haven't used in training. Different file types over time and in different environments. So this was the first kind of innovation that we got to, this kind of cybersecurity analytics approach. Its limitation, of course, is that you have to wait for all the behavior to process before you get the result out at the end. So if you imagine we run it for 30 seconds, we get 30 XY coordinates, which will give us a vector that we can use with a machine learning algorithm to tell us whether or not this behavior is malicious. 30 seconds in, though, if it's something like ransomware, it's not particularly great because you've lost half your files by that point. And so the next step was innovation in the area of trying to detect this earlier. And this is where Matilda's work comes in. So she's actually taken the idea forward of using the same type of data, but with different models that can detect these attacks earlier. And so I'll hand over to Matilda.
Thanks. Hey, hi. Great, it's working. So as Pete said, the previous model using the SOM is great for analytics. If you're in a lab-controlled environment, you can see how a sample is behaving. But what if you wanted to use this on an endpoint? So as we know, static data, Pete mentioned, is easily obfuscated. Even known malware can easily be disguised to evade detection. And researchers have long been in favor of dynamic analysis. But it's not well suited to endpoint detection because it typically takes about 5 minutes per file in the literature and nobody's going to wait that long to find out if they're allowed to open their email attachment. So we wanted to see how early can you tell that a file is going to be malicious. Can we do it in seconds, basically? Because if we can do it in seconds, maybe people are willing to wait that long. And so we used machine activity metrics, which I'll just play this video again because it shows at the beginning. So things like the total number of processes running, the CPU usage, the number of packets being received and sent by each application, and every single second we monitor these 10 different behaviors. If you want to know the details of it, I'm happy to discuss afterwards. We used a recurrent neural network, which is a machine learning algorithm that's really good at processing time series data to try and predict whether or not a sample was malicious or benign. And what we found was that every second we could get a prediction. This graphic on the far side over here is showing you with the kind of wedge of the pie is how confident the model is. And what you can see is that typically the wedge gets narrower over time. That's what we would expect to see because it sees more data and it becomes more confident. And so what was the result of this work? So we found that if you looked at an application for 5 minutes, we could detect 98% of them as malicious or benign correctly. But if we looked at them for just 20 seconds, we could also detect with 98% accuracy that they were malicious or benign, and that after just 5 seconds, we could already get 94 of the predictions correct. And so this gives us a kind of cost-benefit curve of how long you want to wait before you make a decision. So if you're in a strict corporate environment, you might say, okay, everyone has to wait full 20 seconds. But that wouldn't work for every type of workplace. About the time that we finished this research, the WannaCry attack had just hit the NHS. So we thought, yeah, that's a great scenario in which you really want that early detection to happen. As Pete said, if your files have all been encrypted and you don't have a backup, you're basically stuck, or you can gamble to pay your ransom. And what we found was that 99% of the 2,000 ransomware samples we tested were detected within 1 second of execution. And that's basically, I think, because ransomware is incredibly unsubtle in the way that it works. So there are 2 security flaws with this approach, if anyone spotted them. One is that if we only use the first 5 seconds of behavior to decide, and you knew that as the attacker, you could just run Microsoft Word for 5 seconds at the beginning or sleep your application. The other is that it's based on using virtual machines, and there's debate about whether or not it's decreasing, but malware can detect often that if it's running in a virtual machine with more and more inventive ways, it's part of the cat and mouse of trying to disguise that your VM is a VM. But because this process of disguising the VM and detecting the VM is ongoing, we thought the only way that we'll ever solve this problem is just to watch what it does on the target endpoint. You could either try and replicate your target endpoint exactly, but if you have an enterprise with lots of different endpoints, a really heterogeneous network, then you're going to be building a lot of virtual machines and they're going to change over time. So we wanted to see, can you detect malicious processes as they're running on the machine? This might sound a bit mad because why would you let malware run on your machine? But the point is you don't know that it's malware at the time. You've still got your basic static signature antivirus in place, so you're not letting anything through that you definitely know is malicious, but you're watching how it's behaving on your endpoint. What good is it to a user, though, if you get an alert saying, we think there's ransomware happening, all your files are being encrypted right now? One, they have to be sitting at their computer when that happens, and 2, they have to know what to do. So it might wait until the middle of the night, or rather until they detect that there's no user activity going on, or you might be busy and I don't know how, or you just don't know how to deal with that alert. So we thought the only way to sensibly deal with that is that we automatically kill the processes. So you could also quarantine them, put some security restrictions on, but we thought let's try killing them because it's the most dramatic one, and see how that goes first. This is a little bit at odds with machine learning models, because machine learning models will try to do the best they can at matching the data you've given them across the whole data set. So when you're looking at time, if you have a program that runs for a process that's running for an hour, and just for 1 second you thought it was malicious, it's going to kill your program. Even though if you were taking one snapshot every second, that's 3,600 points in time. Only 1 out of 3,600 times did you get the guess wrong. That machine learning model thinks it's really good. It's 0.99999% accurate. But because it's killed your process, it doesn't really matter. So we had to make some amendments to the loss function to basically tell the model that that's what it was doing, to say if you kill a process, you never get another chance to reclassify it as gone. Not only that, but all the child processes are gone as well. So this is with a modified recurrent neural network. This is a kind of diagram of how it works. I'm happy to talk about it more afterwards. But what does it mean to kill a process? So a piece of malware is made up of multiple processes. Maybe 1 or 2 of them are doing the thing that you deem to be causing the most damage. I wasn't going to sit and reverse engineer, nor would I claim to have the skills, the 4,000 malwares in our data set. So we took ransomware again because it's really easy to see the tangible impact on a user, what percentage of your files were corrupted. And what we found was that 50% fewer files were encrypted by fast-acting ransomware when we used our model. So this is running live and including all the analysis and process killing time. And by fast-acting, I mean it starts encryption within 5 seconds. It doesn't need internet access. It's not waiting for some information from a C2 server. It just goes away and ruins your life as quickly as it can. But the model did detect 90% of the ransomware samples. So what we found is the model is basically quite clunky, takes up a bunch of CPU because we're running this on a normal laptop as if a regular person is using this. And so we're working at the moment in distilling it into a more efficient machine learning model. I'm just going to show you a quick live demo of it working. So in a second, somebody's desktop is going to pop up, an unfortunate person. Yeah, I can't speed it up because it just needs to load. I'm not connected to the internet, and it's all in a virtual machine, so don't worry about anything leaking out. So this is somebody running Windows 7. You might think Windows 7, who uses that anymore? The majority of people in the world still use Windows 7. So we can see that we're getting a graph up already, and we're getting predictions as to whether or not the file is malicious. So it already is predicting malicious. It didn't in the first second, and then quickly started to say it's malicious. And I don't know if any of you saw, but all the files on the desktop just got encrypted. So it can work in real time. And what we're doing at the moment is working on making it something that could actually function and that won't kill Microsoft Word when you haven't saved whatever you were working on. Lost the slides. There we go. It's just a bit confused. So part of the work we do, working in an academic research team, but we have very close connections with Airbus and work on site with them often, is that we're thinking about how, we translate research into the operational environment. I think that I need to put virtual boxes maybe. So we'll collect these data sets and train these machine learning models, but often we'll get hold of these data sets in a particular place and also get the test sets from the same location. But when you take a large organization, they're going to get different types of malware and benign-ware than you might capture in the wild. So the types of garden variety malware that a user might come across might be things like phishing emails, whereas a company might get more things that are trying to, steal corporate secret information. So what we wanted to look at was the robustness of our model. So we collected a load of malicious and benign data kindly given to us by the Airbus SOC and wanted to see how that fared when we used one of the models we trained in the lab environment. So the most common data that is used for malware detection with machine learning, which is a very popular area, is API calls. So those are system calls made to the OS to basically get hold of hardware resources. Any process that runs needs to make API calls in order to get access to memory and CPU and create files and things like that. There are a number of different ways to represent them. You might have a binary representation saying, yes, these API calls occurred. You might say how many times they occurred, or you might say these short sequences of API calls occurred. The data we use is slightly different, as I described before. It's things like CPU usage and packets being received and sent and the amount of memory being used. The main difference between these two is that the machine metrics are almost always invoked by every single process that runs constantly. So if a process is running, it's usually using some CPU, or, okay, it could not be, but it's usually has some tangible metric that the model can understand. Whereas API calls get depreciated occasionally, but more often than not, they'll be used more or less according to different trends in software engineering and the evolution of malware in response to vulnerabilities that appear over time or in different organizations. So we hypothesized that machine metrics are basically going to work across two data sets from different places. And what we found for executable files was that that was true. So this graph at the bottom is showing you the accuracy of a bunch of models at detecting malicious executables. The blue dots are from the same, they're collected in the wild. They're publicly available malware, I would say. There's stuff you can get hold of on the internet quite easily. If you were going to deliver from a research team into an organization, you'd say, this model is 90% accurate, and then the people you've given it to have no way of testing whether or not the model is still performing up to scratch. The orange dots are how well the data set we collected were given by Airbus worked. So what you ideally want to see is the blue and the orange dots are close together. The accuracy score that you tell the company you're getting is similar to what they're going to see in operation. And on these three graphs, there are three different machine learning models. We just did three different models to show that it wasn't a problem with the model. So random forest, support vector machine, and the neural network. And what you can see is that the middle three sets of dots are much more tightly clustered together, and those are the machine activity metrics than the API call dots, which show a much lower performance once you put it into production. And interestingly, when you combine the data sets together, it doesn't make the model stronger overall, because machine learning models are quite lazy and they easily get distracted by things that they think are kind of easy markers for telling between the two. So that was what we found. So this is all work we've done around detection and slowly moving from research into how this would get pushed into operation. But what does that really mean for the company? And I'm going to pass over to Pete to talk about how we can translate this information into something useful.
Thanks. So just to wrap up the cybersecurity analytics bit. So I opened it up at the start saying we're including not just the detection stuff, but actually doing stuff with it and informing decision making. So the work that we've done around goal-oriented risk modeling has been translated also into a methodology and a tool. So this tool here you can see is a tool called ICS Model. What it basically represents is, so this is the ultimate goal of an organization. Let's just say, for example, building wings. That depends on certain things. For example, an operational factory production floor, which depends on people and supplies of materials and electricity and all that kind of stuff. So it's very much abstracted, but underneath that you can measure all sorts of things, right? From your networks to the political state of Brexit, doesn't really matter what it is, right? And you can plug this in to these models. The reason you can do that is because this basically is a directed graph, which means you can say this depends on this and this or that, which means it's then useful for conditional probability, which means you could do some Bayesian analysis around it. So if I change the probability of this, it'll update the probability of this, this, and this achieving their goal. Yeah? So if you imagine we then plug that into a piece of work like Matilda's, where you identify very early on an attack on an IoT device, as the confidence grows in that attack, you can keep updating this. So it'll start off at 95% likely of being operational, drop to 90, 80, 70, and so on. So we just keep feeding that in. So this is how this work on confidence, essentially, and labeling from machine learning turns into a probability of a goal being achieved. If you have any questions beyond that, I can answer those later. But this is how we're actually linking work on machine learning to work on goal-oriented risk assessment through a translation of outputs of machine learning into probabilities of goals. So that's ultimately it, other than to say, you know, if you enjoy this type of stuff, there's 2 PhD studentships becoming open at the university very soon. Little plug, it's not really a company, is it? It's for the better good. Everyone needs these people in their organizations. So that's it from us. Thank you very much.
Thank you, guys. Very interesting. Thank you. That was a very interesting talk. We do have a few minutes for questions, but we'll try and get them. We'll
be around after as well.
As well, yeah. I'll speak up. Hi. Yeah, thanks very much for a very interesting thing. What I'm quite interested in is you do a lot of detection of malware, for instance, and the algorithms and the machine learning is detecting malware. But also things like Microsoft Word is quite good at detecting itself and shutting its own processes down. Did you find that you had quite a lot of false positives in your work? Or were you really focused on the malware side of things?
Well, so we've been focused on the malware, really. We've been using malware that would affect Microsoft Office and Word, Excel, and doc files. That's been our main focus at the moment. It's really hard.
Hi there. So you've trained your benign data. How would this transfer to my company? Would I need to train a completely new data set if I'm running different processes?
Well, so it depends. I suppose my view would be that the data are fairly generic data. You know, they're Office files, Word files, but the process would be the same anyway. Even if you had new data, you could just retrain on that.
Is there a code to play with? Can we start playing with this?
Code.
Sorry?
Is there code to play with?
Yeah, on GitHub, there's code which I can give a link to. Yeah.
Okay, thank you very much.
Thank you.